Uh, Basically, today we have to talk about polar coordinates. So let me just start by reminding you of what I think we have used them a little bit this semester, especially when we were doing limits with the squeeze theorem. But okay, here they are. Can everyone see this?
Yes.
Good. Now, oh, this is so. This is okay. Okay. So right, in polar coordinates, you have two variables instead of x and y. They're just r and theta, right? So r is the distance to the of a point, which in this case the point is this red dot to the origin, right? So you see it here. Now I like this animation because precisely it shows you the following. So like maybe I don't know if it's like how standard this convention is, like in Calc 2. But it could have been the case that you were taught about about polar coordinates allowing for r to be negative, right? I don't know. So here, for example, I don't know if you see r equals -4. I don't know if that was something completely common that everyone did. Um, in our world, for multivariable calculus, r will only be allowed to be positive. So really, like the r's that are allowed here are like in this animation, say between like 0 and 4 or 6, right? So here is between 0 and 6. And why is that? Because like the idea is like if you want to go to the other side, right? Like say, what does having like r equals -3 value? It would get you to this point, right? But you can reach this point by still using r equals 3 and just like adding 180 degrees to this angle, right? Is that making sense? So like the point is that you don't need like a negative radius because just by increasing the angle, you can reach the other points that you would have reached with a negative value of r. So really it's confusing to have negative r's. So like the standard convention for us would be that r is always positive. And then if you just want to get anywhere on the xy plane, you just change the angle theta. Is that making sense? So I mean, as you may be clear from polar, like this picture of polar coordinates, like you think of like they give you some sort of radar, you know, this sort of like what you see in like these submarine movies where like they're about to launch nuclear weapons and everyone's dead in the next few minutes. Like you have this radar and then like here's where you are, and then like you see like the points based on this grid. Um, Now, here's like an interesting thing that is pretty obvious from this picture. You have these pieces like, you know, these sort of circular sectors, right? This, which are not rectangles, they're sort of like deformed rectangles, right? Like they're sort of like pieces of a disc. So as like, I don't know if you noticed, but somehow the closer you are to the origin, they're smaller. And as you're moving away from the origin, right, these pieces get bigger, right? So that would be useful in a second because we have to talk how the area gets like the thing that goes into the integral for area gets written in polar coordinates. And you'll see that there's like a factor of r, and that just says that as the farther away you are from the origin, like these pieces of circular sectors become larger or have more area. Okay, so let me start with that on the iPad. So just as the reminder, this is the dictionary that you need to know for polar coordinates. If you have like a point x comma y here, right? And you have r and theta, then the conversions are that x equals r cosine of theta, y equals r sine of theta. And if you want to like, so that's how you write x and y in terms of r and theta. And you can also kind of write r and theta in terms of x and y. For theta, that's a little bit more tricky, but you can also say that r is like the square root of x squared plus y squared, right? And then that theta, I mean, like the easiest thing to say, like there are different options, right? Like, because you can say that the tangent of theta is like y over x. So from here, you can say that theta is like the arc tangent of y over x. You know, but so that's the easiest like way to, that's the easiest way to write theta in terms of x, y, and x. But there are others because, like, for example, you could also say that sine of theta equals y over the hypotenuse, which is square root of x squared plus y. So you could say that theta is also like arc sine of like y over root of x squared plus y squared. And like you could also like you do the same with cosine, right? Like you could also say that cosine of theta equals x over the hypotenuse. And so you could say that theta equals the arc cosine of x over root of x squared plus y squared. Like the last two maybe are written less frequently just because they have like a square root inside the arc, like inside the trig function or the inverse trig function. So that's not that common. Is that okay? Now, so there are like some conventions, as I said, like this one is like more like, so one is like a series, like one that will be enforced like really strictly on in this class, which is like that we will always take r to be positive or zero, right? We're not allowing negative values for r.
Since we're talking about polar coordinates, I want to ask a question pertaining to the recitation, because when we were going over recitation, one of the example problems included something to do with symmetry. And then during lecture, you said that we need to be careful with symmetry because you don't know what's happening with the actual graph. Well, yeah, with the actual function. So I'm kind of trying to understand, do we need to implement symmetry or do we don't implement symmetry?
Like my recommendation with symmetry is that no problem will actually require you to use symmetry, right? So it is best avoided because, like, for example, it's like, you know, the thing is like people can take a lot of freedoms when they use like symmetry arguments.
Yeah.
So if you're like an expert in symmetry, then sure, you can use symmetry and that's fine. Like the thing is like, you know, sometimes like it's like sort of like what I was saying. I don't know if I said this in class. Imagine that like the problem was like to find the mass like of this half disk, right? Or something like that. You can say like, I agree the figure itself is symmetric with respect to the y-axis, right? But if you have to find the mass because I gave you like a density function, right? Like I gave you some density function. if the density does not happen to be symmetric, right?
Yeah.
Then you can no longer apply the symmetry argument, right? Because then there could
Yep.
be more mass on one side than the other. So the problem is that symmetry not only requires you to look at the actual figure, but also at the actual function you were working with. And so that's what I think is like not the best idea to do in this class. I mean,
Understood.
none of the problems will require you to use symmetry. Let me put it that way.
Yeah.
I know
Okay.
that physicists love using symmetry for when they compute moments of inertia and other things in class, which is fine because like the physicist pictures are like all perfect. You know, they have like this uniform density distribution or whatever, and so that's fine. But like for us, like if it's just like a weird random function, then
Got it.
like for example, here's like another like this is like an idea of like symmetry. Like say, imagine that you had like a Lagrange multiplier, right? Something like this, where you have to work with these equations. Right. I don't know if this really makes sense or not. Let's say that they do.
It does.
Like, if you think about it, actually, X and Y are sort of playing the same role in the sense that, like, you know, here they are both being multiplied with one another, and here like their squares are being added. So actually, this is like what I'm trying to say is if you actually understand symmetry, you realize that the answer that you have to find will give you like essentially the same value, like the X and Y are sort of indistinguishable variables. So like the answer sort of has to be symmetric with respect to X and Y in a sense that could be made precise. So that sort of tells you that like if you find like an answer where like Y equals 3 times X, that probably there's something off there, because there's really no difference between X and Y in the way they are appearing in these two equations. But you know, like that sort of argument is like, again, like more sophisticated, so it's better just to do the system of equations with Lagrange and just let it and just find whatever it tells you the answer is.
Okay.
Yeah,
That's fair. Thank you.
Sure. So as I was saying, like sort of like a strict rule for us will be that R is non-negative, and then like a more flexible rule will be that theta would take it between 0 and 2 pi. Because, you know, sometimes it's also useful to write theta between negative pi and pi, but usually all the problems, like you can just like assume that theta is between 0 and 2 pi, but like you may even see on MyLab on occasion that you have to enter sometimes negative angles, but and so that's okay. That's less that would be more common. Like the one that we will always use is that R is non-negative. That's for sure, 100% of the time. This one, it won't be 100% of the time, but every problem you can just do with this assumption for theta, basically. Is that making sense so far? So good. Any questions about this? Now, if you think about double integrals, now here's the fun part. So let's remind ourselves what double integrals are in Cartesian coordinates. So if you think about it, like the stuff that I was writing up to this point has been some junk that you put here on the bounds, and then you would write something like dy dx, right? Or if you use the opposite order of integration, you would put the function like some other bounds, and then you would put dx dy, right? So I didn't make a big point out of this thus until now, but if you think about dy dx or dx dy, right? Let's focus on this thing for a second. Well, like the point of those things is that if you had like the region of integration, like, you know, it's like some hype, like some mutant region. So you had these like lines here, right? You start cutting it. And well, if you think of let's see where I should draw this. If you think of this as having like some width dx and some height dy, then you get this tiny rectangle which has area dy times dx, right? So here there's some tiny area dA, which is dy dx, or dx dy, that's fine, which is the area of a rectangle. Oh yeah. Like if I actually gave you equations, well, maybe this is really, you know, it's possible that this could be done with, depends. Yeah, definitely if you were to use, it probably would require a couple of double integrals. Yeah, depending on how the equation is written. But my point is that you see, like dy dx or dx dy, they're not like arbitrary things that you write on the integral, because they're trying to convey the idea that this sort of represents like a tiny piece of area. Is that making sense? Yeah, that's exactly, that's what I'm doing. But now what's going to happen now in polar coordinates? Now in polar coordinates, like something similar we should try to do, but now we, you know, it's sort of like this radar that I showed you on the application, on the animation, right? Like when you have like polar coordinates, like if you have the same mutant region, the region is not broken sort of into rectangles. They're broken more into these sectors that I show you uh, on GeoGebra. So what I'm trying to say is that in polar coordinates, so what about like, so what's the area in polar coordinates? Again, if yeah, they're like pieces of pie, good. So and let me try to at least use two colors. So, you know, you could have like this, you have like basically the way in which polar coordinates are built is like you have these circles, and then, oh, pieces of pie also, right? So, and yeah, that could be interesting. I don't know, I don't doubt that there's like a linguistic reason for why they're written almost the same way, but it's a nice coincidence. So you see, do you see like the difference? Like these are not quite rectangles, right? So let's try to focus on one of these pieces. Let me focus on this one. And let me do the picture separately here, so that I just draw that piece. So here I'm zooming into this piece that I did there. So the idea is that this piece, you know, let's say this starts like at an angle, this first like arc, this green arc is some distance r from the origin. So let's call this r. Right, and to move from this ray to this ray, you have to move some amount theta. So usually that angle that you moved is called let's call it d theta. Right, so anyone remembers like I don't know if anyone remembers like what's the length of a part of the circle, what's the length of an arc of a circle? You know what I'm trying to say? How much does this measure? Yeah, r time. You're right. Like if you use radians, that's the reason why you use a radians. Like if you use radians, this black arc measures has length equal to r times the angle. But in this case, the angle is the theta, right? So this has length r times the theta. Is that making sense? So the black arc that I just drew has length r times the theta. And let's say that between these two arcs, there's like you move the distance by an amount dr. So there's like some dr here. This purple region has length dr, right? And so now what you can do is, you know, sort of you start making copies of this black arc. So you see, like you sort of move this black arc along towards the other arc, and it doesn't quite fill out the entire blue region, right? Like there's some leftover stuff here. But the point is that this, like, what would be the area of this black stuff? Like you just move this arc by an amount dr, right? So the area of this black thing should be like just r dr d theta. Is that making sense? Yeah, but now we're doing it in the adult version.
Has anything changed yet from what you've shown us from Calc 2?
I think in Calc 2, if I'm not mistaken, like usually you would set it up just as a single integral of from theta 1 to theta 2, and then you would integrate like r squared over, like, you know, right now I don't think there's much of a difference, but the way maybe in which I will write this as a double integral will make it look different. So
Okay.
but yeah, it should be almost the same as what you saw in Calc 2 for now. So, but you see, like what I'm trying to say is that sort of the area of this piece is not quite the same as the area of the entire blue sector, but the difference sort of in the limit goes away. So like the really small area that you care about that goes into the integral in polar coordinates is the following. And this is what you really need to remember of what I just said. So the analog of the area in polar coordinates is just r. Sorry. Well, it could be. I mean, it could be r d theta dr, or r dr d theta. This is how it gets written down. Okay. I mean, right, like there's a, like what I'm saying is that like you sort of, like what I'm saying is that you sort of started with this angle, you sort of took that arc, that black arc, and you sort of make copies out of it, right? And so essentially, you know, you make copies of it by an through like an amount dr. So roughly the area is just, I mean, it is not 100%. There's an error term, like that's how I should say it. There's like actually like some sort of error term in the formulas that I'm writing, but sort of in the limit they just go away. Like in the book, it's sort of like they keep track of everything. Like if you actually want to compute all the formulas, but I'm just saying like this, like there's some junk that is not captured by these formulas, but you know, so I should have said like the roughly the area of the black rectangle is like approximately equal to what I wrote here. Yeah, everything is like an approximation, you know, like with limits.
Is this related to kind of the things we did with the frustum when we were trying to find the arc length? It's like the radius, the small radius and the big radius don't really matter because the kind of dx is very small. So
Well, I don't remember. Did we do the frustum or you?
this is Calc 2 related.
Oh yeah. I mean, this is similar. Like, okay, what I'm trying to do is like similar to, you know, when you do like when you find the derivative for x squared, and so you may say something like this.
But the delta x is very small, so it's just x squared. Okay.
Yeah.
That makes sense.
Like, so what I'm saying is that if you actually do the calculation, there will be a bunch of junk terms that involve like delta theta square or other things, but they just in the limit go away. And so that's how you end up with this formula in the limit. But this is the one that you want to use, like. Okay, so like what that means is that in polar coordinates will like, so in polar coordinates, like our integrals will look like this. So like what I'm trying to say is that if you compare this like with what happened in the Cartesian case, sorry, just to go back, you had in the Cartesian case, you had the function and then you just have dy dx or dx dy. In this case, you still have the function, but now you have like, instead of just dr d theta or d theta dr, you have this extra factor of r, which is multiplying these other two quantities. Okay. Right, yeah. Well, there's also like another reason why this formula also makes sense is that if you had like, I'm about to write it again, but if you had no r here, right, like theta has no units, right? This like, because it's like a part of, it's a tiny piece of radian or angle, so that's dimensionless, and so you would get something here that has like only units of length because r does have length, right? So you have here, you get length and then you have length, but that cannot be equal to area, so you have to multiply by r to get something with units of area. Is that making sense? That's what people call dimensional analysis. So you need like a factor of r so that like this would actually have units of area. That kind of gets you a long way when you have to figure out these formulas, actually. Yeah. That also tells you it could not have been like r squared, because r squared would have given you like units of volume, for example. Okay, and then so we're almost there. now we just have to do the analog of the horizontal or vertical arrows. So that, like, let me explain that. And that's like the important thing in polar coordinates. So what's the analog? So the analog in polar coordinates for that are actually radial arrows. So this is now we're going to do. So what I'm trying to say is that, for example, if you had this region, oops. Imagine that you had like a region like this. Okay. So before in Cartesian coordinates, right, if you had wanted to analyze this region in the past, you would have used arrows which were either like this, right? Or arrows which were like this, correct? Well, I think, I don't remember which colors are, maybe I'm flipping the colors, but they were like something like this. So they were either parallel to the X or Y axis, right? Those were the types of arrows that we used before. And so these were like the Cartesian arrows. But the polar arrows, like the way in which they get drawn, is just by, you start at the origin and like literally think of this radar stuff where you have, imagine that you have like a laser pointer at the origin. So with the laser pointer, you start pointing like at different places on the XY plane. So imagine that you have like a laser here. Okay, so essentially what you do is you sort of look at where the radial arrows or radial lines enter the region and where they exit the region. Okay, so let me write that, and like we're about to do some examples so that people so that this is more clear. So the idea is that here, we would write something like this. So like, oh, sorry, I forgot the R. So if you do the integral in this order, what you put here like is the equation where the radial arrows enter the region. And so here, this is done in terms, like this equation can depend on theta. And this is the equation where the radial arrows and exit the region. Okay. And then here you put like the smallest angle of theta. And here you put the largest angle of theta in the region. Okay, so let's do some warm-up exercises. Hopefully to try to make it more clear. I mean, it behaves the same way. It's just that instead of drawing vertical or horizontal arrows, you just have to draw arrows that start like, which are radial, which look like more like rays of light, right? They start at the origin and they just like, you look at where they hit. So yeah. They just like are like arrows with some inclination, like angle of inclination, right? Like some tilt, but let's try to set up like an integral. And here the region will be the part this is like, I mean, here one just needs to be like, do the arrows carefully, but you'll see it's not that bad. Okay, let's try to make the picture. So that's one circle, right? And then there's this other circle, which is of radius 3. Right, and then we're looking at the stuff between the two circles in the first quadrant, right? So the region of integration is this stuff. Is that making sense so far so good? Like first one needs to understand the region, right? So is this okay?
Yes.
Now, in fact, if you think about it, this would be a mess if you try to use Cartesian coordinates, because like I will erase it. Oh, let's do this. Like I'll erase this in a second, but you see, like if you were to do vertical arrows, like you would get something like this. Like, you know, like you have to split it into two regions, like one for like things like that, and then for these arrows, right? Like, so if you want to do this like with vertical or horizontal arrows, you sort of have to write those at least two double integrals, because there's no, you know, it's not like that easy in Cartesian coordinates, but in polar coordinates, you will see that it's a lot more simple. So the first, and again, like maybe you already did this to some extent in Calc 2, so that's good. But what's the first thing that you should do is rewrite the equations in polar coordinates. So how is this equation rewritten in polar coordinates?
R sine squared plus R cosine squared is equal to 1.
Indeed. Now you can do that but also every time you see x squared plus y squared, you can just go to the initial dictionary and you say immediately that just r squared. That's like what which you get by squaring these two. Like, let me write it here. In fact, you know, because cosine squared plus sine squared equals 1. So you can just write here that this is the same as r squared equals 1. Is that making sense? Or the same as r equals 1. And that's another way of saying that that's a circle of radius 1. Is that okay? Good. So this is the equation for the first circle in polar coordinates. This is the equation for the second circle in polar coordinates. Okay. And then, so if you wanted to, write the integral in polar coordinates, for this thing, okay, what I told you to do is that you have to draw like radial arrows. So imagine that you have, like, again, you have like a laser, and you start pointing from the origin to this region. So it's almost, or you just think of it like as a light bulb, right? That you have at the origin. So there are rays of light moving in all directions, and we're just trying to find where the rays of light hit first, like this region, right? So where do the rays, through which equation do the rays enter? Yeah, like flux circuit. Where do they enter first, like this, the yellow stuff? Good, they enter through r equals 1. So you should put here r equals 1. And there, where do they exit? They keep moving through the yellow stuff until you get through, right, they all exit through the bigger circle. So they exit through r equals 3. Is that okay with everyone? And then for theta, you're supposed to put like the smallest value of theta in this region and the largest value of theta in this region. So what's the smallest value theta takes on this region? Yeah, it's 0 to pi over 2. Yeah. Is this okay with everyone? Because you go from the x-axis to the y-axis, and that's your first integral in polar coordinates. And we're almost done, because we still have to think about what to do with the function, right? So what was the function? The function was x times y, right? That's the function I gave you in this example. So what do you need to do to this function? You cannot just write it as x times y, because then you're combined, like, you know, you have to stick to either working with polar or working with Cartesian coordinates. So you have to rewrite this x times y as in terms of r and theta. So what do you get when you write it in terms of r and theta? You get r cosine of theta times r sine of theta, which is r squared cosine of theta sine of theta. Is that okay? So really, like, the integral that you have to do is the integral from 0 to pi over 2 from 1 to 3 of r squared cosine of theta sine of theta times r d theta.
Can you explain f equals xy one more
Oh,
time?
that was just because in this particular example, I told you that this is like the function that we were going to use.
Okay.
Yes, it could be right. It could have different expressions, right? But it's just to make something concrete so that we can actually integrate this.
Thank you.
Is that okay? In fact, but like I wrote it later because, like, again, the point is that these bounds are found the same way regardless of what f I would have given you, right? Like, these bounds are sort of just specific to the region. They have nothing to do with the function, but just to do like the integral, let's use this function in our example. So in this example, f happens to be x times y. Is that okay? So now we have to do this integral.
Pastor, just a quick question before you move on. Say the
Mhm.
purple and the red circles weren't uniform.
Uh-huh.
In that case, there would be like an equation for the r equation. So for the inner integral, that would be like some sort of weird equation.
Indeed, yeah, we'll do that in the next example. Yeah.
Okay, good. And those would be usually given, right? We wouldn't have to find, because I can't imagine how we would find one.
They would be given, but typically they're given in Cartesian coordinates, and then you have to convert them to polar coordinates. But yeah, I wanted to do like an example that would start like easy, where like, the bounds are constants. But yeah, the next one should be more interesting. Yeah.
Pastor?
Yes.
Where did you get the r squared cosine and sine theta?
This thing.
Yeah.
It's just that, I mean, we're trying to integrate a particular function so that we get like a number. So for this example, I told you, let's use this function, x times y, right? Just as an example. But like the idea is that you cannot put x times y inside the integral, right? Because you should put everything in terms of r and theta. So what I did was rewrite this x and y in polar coordinates. Is that making sense?
Yeah. Okay, I got it. Thank you.
Yeah, so here's like what I'm doing. Just to have something concrete. And also because, like, I'm not sure, like, just to convey the fact that this will get integrated sort of in the same way. So because we're doing the integral first with respect to r, you're supposed to treat r as a variable and then like everything involving theta as a constant. So what's the integral of r cubed dr? That's r squared over 4, right?
Yeah, okay. You said r squared, but yes, r cubed, as you wrote.
Right. r fourth over 4, right? Yeah. Good. I wrote it well, but I said it incorrectly.
So in regards to this particular example, what would be the input region? And then obviously the output is when we convert the given function f equals x, y, but what would be the input region?
Well, I mean, like the input region, like if it was just like this stuff between the circles, right?
Okay.
And then, like, I mean, you get like, you're always, I mean, if you actually want to compute something and not just like write the bounds, you are given like an input region and an input function, right? So this was the input region and this was the input function, right?
Right.
Is that making sense?
Yep.
Good. And then what's 3 to the 4? What is that? 3, 9, 81, 2. 243. Is that what 3 to the 4 is, oh, no, it's 81, right? Because, good. I did 3, right, yeah. It's 3, 9, 27, and then 81, good. So it wasn't that bad. Okay, it's not that bad. So, and then you have to do the integral from 0 to pi over 2 of cosine of theta, sine of theta, d theta. I don't know if anyone remembers how to do this integral from Calc 1. You can make a substitution.
Yeah.
Yeah, that's what you were going to say. Yeah, you can make, like, for example, u equals sine of theta. Yeah, and so if you make u equals sine of theta, then du is cosine of theta d theta, right? Okay, so this 81 minus 1 over 4, that gives you 20. And then here, like, so this becomes 20, and then like this became sine square of theta over 2, I think, right? And so this is what you're integrating from 0 to pi over 2. So you get 20 times 1/2, and so that's 10. Is that making sense? So that's the answer in this case.
We're not going to have cases where it's like cyclical trig integration, like in Calc 2, will we?
No, I don't. Usually a substitution would be enough, or worst case, like integration by parts, but that's more unlikely. You know, I think I know what you're saying, that sometimes you got to do twice integration by parts, right? Or like, I don't know. No, that probably not. Substitution should be enough most of the times. There might be one that requires integration by parts, but typically that's like with exponentials, not with trigs.
Trig substitutions rather than u substitutions.
Right. Oh yeah. No. Like nothing too fancy. Yeah. Good. Well, the next example should help you. Let's do the next example. That will should help you clarify this thing about how to find the bounds for theta in other situations. So let's move to the next one. So is this okay? Are there any other questions about this one? Are we good? Okay, this is another way in which you might see the problem written, so that's good to know. So another way in which you may see these problems is that they give you like a double integral in Cartesian coordinates, and from there they ask you to rewrite it in polar coordinates. Oops. Yes, that's one of the things we need to do. Everything needs to be changed, right? Because you cannot keep, like, if you move to polar, you can only see r and theta in the answer. So you cannot, I mean, the bounds are the same, but they have to be rewritten in polar coordinates. So it's not just changing y with r sine of theta. That wouldn't be too easy. Although that's something that you eventually need to do. So like actually the first thing that makes sense to do here is to rewrite everything. I mean, to find the picture this region corresponds to. I don't know if you have realized, but if you don't have the picture here in these problems, you cannot do anything, or you can do very close to 0. Like, you know, you need to have the drawing somehow. If you can try to do it on in your head, but that's too risky. That's similar to the symmetry arguments. Like you're doing Russian roulette. So let's try to. Let's try to find the region first. Like if you think like this is not too bad. Like this is using vertical arrows, and like the equation y equals 3x is just like the equation of a line. So here you would have like y equals 3x. Right? And then here you have 0 and 1 for x. And so essentially the region that we're looking at let me do a different color. Essentially, the region we're looking at is this triangle.
Is this the same triangle that gave us the unsolvable integral before?
Well, I think in that one I had used y equals x, but it more or less it's essentially the same, right?
Same properties.
It's right. It has it's essentially the same shape, right?
Okay.
But like the point, like the important skill here is just like how to reinterpret this double integral as a picture, right? So once you know that, like you again are on the right track. And here's the thing. What you need to do now, let me put y equals 3x. Like always do this. And let me erase this here just for a second. Oops. Like the thing that you always need to do is rewrite the equations in polar coordinates. So let's try to see if we can rewrite y equals 3x in polar coordinates. How would you rewrite this in polar coordinates? What do you do here? What does y become? R sine of theta, good. And 3x becomes 3r cosine of theta. Is that making sense? What else now? And then you try to start simplifying this. What simplification can you do for this equation? An obvious one. You can cancel the r's, good. And so you get sine of theta equals 3 cosine of theta. Right? And what else can you do here? If you want, now we're getting close to the end of this equation. Like it's better just to write this with a single trig function. So you can say that the tangent of theta equals 3, good. And actually there's no special angle that gives you 3 as tangent, but you can then just say that theta equals the arctangent of 3. Is that making sense? Because like that's not like 45 degrees or 30 degrees or 60 degrees. It's just like some angle. We don't know what particular angle that is. I think
So,
is there? Or is
theta equals arctan of 3. That would be the maximum angle, right? So that would go.
right, exactly. This is like this big angle is arctan of 3. Yeah. Is that right? Is that okay? Well, yeah, you have to do more for the exam than that. But is this okay how the conversion was made? And this is also related to the question before in the chat of how you would find the angles if it's not like the first quadrant, for example. You just have to take the equations and start simplifying them as much as you can, and then like the relevant angles will appear. Okay, so let's try to convert, like, and now here comes the conversion piece. Okay, so the first thing that you have to convert, I don't know if you still see like above, here we have the y was the thing we were integrating. That has to be converted to polar, so this becomes r sine of theta, right? Then dy dx, right? This is like dA, right? This one's the same as dA, but remember that dA gets written in a different way in polar coordinates. It always gets written as r dr d theta. So you have to put here r dr d theta. Is that okay? Is that making sense? So that's the conversion of the stuff inside the integral. That's how that stuff gets converted into the integral. And then you have to start putting the bounds. And for that, we use the picture. So now what you have to do is, again, draw these radial segments or radial arrows. Right, and you have to check where do these arrows hit first the yellow region, right? Well, they'll hit from the origin, right? They'll start at the origin because the vertex of the triangle is at the origin. So here you can put r equals 0 as the first bound, as the lower bound, right? And where do the arrows escape? Where do the green arrows, radial arrows, escape the triangle? Through which equation? Well, it's not x. I mean, this is where you have to be careful. They all, like, let's use colors. They escape through the brown segment. Is that okay? They escape through this side of the triangle. Is that making sense? Okay, everyone is close to the truth without getting to the truth. So, like, what's the equation of this brown segment? What's, like, in Cartesian coordinates? X equals 1. Good.
Oh, okay.
What is x in polar coordinates? R cosine of theta, right? How do you use this equation to solve for r? What like
1 over cosine
1 over
theta.
cosine, which is secant of theta, right? So they escape this, like, arrows escape through r equals secant of theta. Okay. Is that okay? Just make the picture. Like, this is where, like, if you make the picture and you use different colors, you don't get confused. But you have just to take it one at a time, you know. And then, and this is fine because if you remember the rules of the game, I told you the bounds that you put here can depend on theta. So this is okay. So they are no longer constants, right, as in the previous example. But if they're not constants, they can be functions of theta. So what's the formula for, like, what are the values for theta? What's the smallest value that theta takes in this triangle? The smallest value is the x-axis, right? Which corresponds. Oh, good question. So the thing is, like, well, there are two ways to answer it. Like, we are only going to use the method where we do dr d theta, right? So we're always going to use this order. It's less symmetric than in Cartesian, where we could use vertical or horizontal arrows. We're going always to stick with this one. The way in, like, the reason why I knew I was doing it this way is because, you know, along each of these green segment arrows, r is changing, right? R is the stuff that's changing values. Theta is, the angle is fixed. So r is the one that's being variable first. And so that means that you're integrating with respect to r first, if that makes sense. So on each of these green lines, r is changing, and that's why you integrate first with respect to r. But we're never, like, doing the other order of integration. It's just a little bit more complicated, and it's not very useful in polar coordinates. So we're never going to integrate, like, with d theta dr. So yeah, at least that's a good thing about polar coordinates. You always, like, we always stick with this order. So you only need to worry about drawing radial arrows. Is that making sense? Good. And after that, you can integrate it if you want. But here it was more like a question about setting it up. Now let's try to do something which is also more interesting, maybe. Which is the following. Now let's change a polar integral into a Cartesian integral. So change
I just want to double check that the purple terms from above, are they related completely by color, or is?
Oh, sorry, this was a stupid color. Yeah, this should have been, yeah, they're completely unrelated. So let me, yes, there's no. Excellent.
Okay, thanks for the clarification.
No, that's a good psychological thing to, yeah, good. Now it's better, thanks. Okay, now this one is a little bit more interesting because now I give you the integral in polar coordinates, and I want you to convert it to a double integral in Cartesian coordinates, okay?
We just start from the bounds and kind of figuring out what the shape is.
Exactly, that's the thing, right? The bounds for theta are not that bad. Like 0 to pi over 2 means that all the action is taking place in the first quadrant, right? So that's good, but like what we have to figure out is what this upper bound is, because r equals 0 is also clear, right? But so let's try, yeah, as you said, we have to start with the drawing. The drawing is everything.
So then it would be kind of the graph of cosine theta in the first quadrant, right? And then it would be
Well,
the rays from the origin to that drawing.
Well, is that we're not graphing, right. Like the thing is like the graph, like I agree. If you were drawing like theta and r as the axis, then you would just draw the graph of cosine, right?
Oh, right, okay.
But you're not doing the graph with respect to r theta. You're doing it with respect to xy.
Okay,
Is that making sense?
yeah.
Yeah. No, that's like a good point. We are looking for the pictures on the xy plane. Later in the course, we'll do something called like Jacobians and change of variables, where like we actually do the graph with respect to new variables like r and theta, and then you would draw just like the graph of cosine. But that's not what we're trying to do right now. So what's the, like, my question is, how does this equation look like on the xy plane? Well, this is not really y equals x. That's a little bit more complicated. That's not.
Multiply both sides by r.
We need to go to the dictionary. What's r? R is the square root of x squared plus y squared, right?
Can you just, would it be easier to multiply both sides by r?
Yeah, you can also do that, but I mean, like that maybe look like a trick, and like you might be like, okay, how would you would have guessed that, right? At least this looks more like straightforward, right? And then what is cosine of theta? Go back to the dictionary. Cosine of theta is x over root of x squared plus y squared. Is that making sense? It's not also, it's not x equals 1. You have to be careful. Like one needs not, don't jump ahead. Yeah. What do you do when you see this? Like you can multiply both sides of the equation by root of x squared plus y squared. Is that okay now? And anyone recognizes this shape? It's a circle if you complete squares. So this is x minus 1/2 squared plus y squared equals 1/4. So if you go to xy, you had a circle center at 1/2, comma 0, a circle radius 1/2, and if you look at the picture, we were looking at the stuff in the first quadrant because theta was between 0 and pi over 2. So really the region of integration was this one. Yeah, it's tricky. This one is tricky, you see. But like if you think about it, now that you have the picture, like the bounds make sense because what are the bounds in polar coordinates for this yellow region? Well, all the rays start at the origin. So they start all at r equals 0. Which is what you see here, and they all end at the equation of the circle, but the equation of the circle, like we just saw, that is the same as r equals cosine of theta. So it is, and then like this circle is on the first quadrant, so it's from 0 to pi over 2. Is that okay? Okay, you're almost there. Like we have the picture now. Let me rewrite the integral in polar coordinates.
The question is to transform this into Cartesian coordinates, right?
We wanted to transform this into Cartesian coordinates, right?
Okay.
Yeah. So now how would you transform this? Like we can even find the bounds now and then worry a little bit later about what we want. Okay, like there are different ways to do this. Like here's the thing. Well, let's say, let's say in this problem, I wanted dy dx just to make it easier. Okay. So here's a first thing that you have to realize. Remember that dA is dy dx, or let me write it here. Remember that in dA is dy dx, or r dr d theta, right? So if you, in this case, because we all are only seeing like, and I think I'm almost done, but I may need like 2 more minutes after the class is officially over. So like you can watch the Zoom recording if you need to leave. But you see, like here you have the r d theta. So the r d theta is just really dA over r. So this is the same as 0 pi over 2, 0 cosine of theta, 1 over r. And then this becomes dA over r, right? Is that making sense? Because like you just have here dr d theta, you don't have r dr d theta. So you need to, I mean, I'm just saying that like, you know, in polar coordinates, the dA is r dr d theta. So if you divide by both sides, you get dA over r equals dr d theta. Is that making, maybe that's better now. So so really, this is like how the like integral and polar coordinates could have been written. Okay, but what is r squared in Cartesian coordinates? What is r squared in Cartesian coordinates? X squared plus y squared. And then remember that dA in Cartesian coordinates is dy dx, for example. So now the only thing that we have to do is find the bounds. So what are the bounds if you use vertical arrows for this region?
So would it go from, since the dy is on the inside, we need the x dependent bounds, right?
Right, you need the x dependent bounds, correct. But
So
we have
then
the equation of the circle, right?
Yeah, so wouldn't just be the square root of that.
You have to solve for y squared, right? If you solve here, you can say that y squared equals 1/4 minus x minus 1/2 squared. And so y equals the square root of that. And so that's the bound for y. It's from 0 to that square root. Is that making sense? That's the equation of the circle in terms of y, or like or it's y as a function of x. And then the x just goes from 0 to 1. Is that okay?
That makes sense. And the double integral of 1 over r, that's just the original
Right,
polar coordinate given.
The 1 over r was the original function example thing that I gave you. Yeah.
This kind of stuff doesn't require a lot of CPU power. It's more like RAM.
Yeah.
RAM intensive.
I mean, once you get to the picture, it is not that bad because the picture will guide you. But if you don't have the picture, then you're really like, you won't get it like that far, right? So yeah, like figuring the circle out, like figuring that this was a circle was not easy, right? It's not that straightforward. You have to be, you don't need to jump ahead and do like a lot of crazy simplifications, because otherwise you find like equations like are completely different from the one that you actually need. Okay, so but like this will keep reappearing because like next week we have to do triple integrals, and you'll see there's like one that is called cylindrical coordinates, which is secretly like polar coordinates, but like a 3 version of that kind of. I mean, it involves some version of polar coordinates. So next week we'll start talking about triple integrals. Yeah, which is and then and yeah, I'll see you on Monday then. Oh, how much should I scroll up? Good, good. Bye. Bye. See you.